We'll share the desktop. We are. Okay, so welcome back from Easter break, and let's go ahead and get started. So we have Daniel presenting on Unix. Are you ready to go, Daniel?
Sure. How do I get the control on the screen?
You should be able to just replace it with what I am doing, but I can also stop my sharing, but you should be able to just replace it.
Okay, I just send request control.
Okay.
Can y'all see it?
No. Let's see. Is anyone else seeing it?
No, I think you need to hit the screen share button.
Share.
It's the rectangle representing the screen with the up arrow. Yeah.
Yeah.
Right in the middle. To the left of the ellipsis.
Share?
Yeah.
Mm-hmm.
Click on that, and then it'll allow you to pick from your applications and your screens.
Okay. All right. So, has everybody seen the Bible verses?
Yes.
Okay. So my devotional is actually 2 verses. We just got done with Easter, and so the first verse is John 15:13, and says, "A greater love hath no man than this, that a man lay down his life for his friends." And the second verse is 2 Timothy 1:7. It says, "For God has not given us the spirit of fear, but of power and of love and of a sound mind." Like I said, this is probably the weirdest Easter any of us have really come across, I'll have to stay at home, either live stream or watch the services on YouTube or however your church is doing it. But in the middle of this pandemic, it is important that we not give into our fear. Because of course, God has died for us and he's not going to turn his back on us. And that's pretty much all I have for devotional. I did have something else in mind, but then the pandemic kind of made it all moot for a bit. So, all right, let's go and get started. Okay, is everybody seeing the PowerPoint?
No.
No. Yeah, let me just do this here. Share. Here we go. Can you see it now?
Yes.
Okay. So the original plan was that Darshini was going to talk about its origins, how Unix started. Kim was going to talk about where we are now, and I was going to talk about what was going to happen in the future of Unix. But of course, I don't think Kim is able to really attend these meetings, so I've kind of changed it up a bit. So the future of Unix, where we are at now and where we are going. Of course, Unix originally was BSD, done by the Berkeley Software Distribution. It was based on the original Unix. It was kind of what everybody was using. If you used Unix, you were most likely using BSD. Now it stands for Unix derivatives such as OpenBSD and FreeBSD. And of course, Beastie, which is kind of a pun on the name BSD, is the official mascot. Just before COVID-19 hit, I actually went to a thrift shop and I found I found a manual on Unix, and there was actually BC there on the cover. So he's been around for a very long while. I think he might actually be around longer than Tux, but I could be wrong on that. Okay, OpenBSD. This one is actually known as being one of the most hard operating systems. Is on the default install, you cannot break into it. It was designed for simplicity. Only 2 vulnerabilities were found since it started. Like I said, it's been considered one of the most hardened operating systems around. But unfortunately, not much works with it outside of some open source apps. FreeBSD, it's very similar to OpenBSD, but you've most likely used it without knowing. Many video game consoles and a lot of Apple devices use it. Licensing uses for free use, which is why a lot of companies use it. I actually believe that the Macintosh uses FreeBSD, but they have like OS X running on top of it. I know for a fact the Apple Watch uses it, and I know also for a fact that the PS5 is most likely going to be using it. Now here's Linux. Now this is something that I find that a lot of people get a little bit mixed up on. Linux is not exactly the same thing as Unix. Linux is the kernel. GNU is the operating system that runs on top of the kernel. And GNU is actually a recursive name that stands for GNU's not Unix, because Richard Stallman really wanted to push that point home. I'm not sure how he came up with that name, to be honest. It may still be the future of Unix because it has like a lot of the same philosophies. And while Unix is still used in a lot of other things, like, of course, Apple computers and video game consoles, I think that with the support behind Linux is basically what's going to drive it further into the future than a lot of the other Unix versions. System D defies the one program for single tax philosophy because it does, last I checked, like several dozen things. You can actually use it as a bootloader, I hear, as well as like loading up your networking and a whole bunch of other random stuff. So if System D goes down, pretty much the entire thing goes down. It's kind of a single point of failure. But like I said, it still carries a lot of the same philosophies as Unix, besides the System D thing. So what's next? FreeBSD is everywhere, and like I said, it'll probably be used with the PS5. Linux is also used everywhere. It's used heavily in systems like Android, Chrome OS, and to my knowledge, most servers use Linux because you don't have to pay a whole lot of licensing fees. Red Hat is a version of Linux that you pay a license for, but it also has like some of the best support. And now gaming is also becoming viable for Linux because Proton has come out by Valve. Same people who did Portal 2 and Half-Life. It's kind of like a compatibility layer, so you can run games like Skyrim, Doom Eternal, all these on your computer if it uses Linux. OpenBSD is mostly used on internet routers and it's probably still going to stay that way. Not very many people I know use it on desktops. I've been tempted to use it for fun, but at the same time, almost nothing really runs on it, so I decided to pass. So, is there any questions?
All right. Well, great job, Daniel. So I guess one question that I did come up with is, so Mac OS, I keep hearing it was built based on the Mach operating system. Does that mean that Mach was based on BSD as well? I think that might be the case.
I've actually never heard of Mach.
Okay. It was the operating system for the next company that Jobs created when he left Apple, when he was kicked out of Apple before his return. So you're probably not familiar with the Next computer as well, and I believe that's where Mach OS came from. Or yeah, that's the company that produced Mac OS X. I mean the Mach operating system, which was then used when Apple wanted to upgrade their operating system and realized that what they had was not doable to move where they wanted to go. All right. So let me go ahead and take over the sharing now. All right. So Mr. Kim will probably not be presenting because, again, he's having problems connecting in from I believe South Korea, but where he is. And next will be Ubuntu with Jason and Bailey. And follow that by that is Mac OS X from Tyler. Schedule pretty much the same as before. Wednesday by midnight, Chapter 6 CPU scheduling quiz. I'm hoping this is not too much of a workload on you because it is open book and open note. So you should be able to glance quickly through the chapter material and not study real hard, take the quiz, and be able to to do well on it. Monday, April 20th will be the quiz on Chapter 8 by midnight again. And then Monday, April 27th is when the Chapter 10 mass storage programming problem is due. And Monday, May 4th is the Chapter 12 programming exercise, which is extra credit points. And we'll go on to page replacement algorithm examples that I was presenting and the virtual memory lecture notes, or the lecture on that. We'll finish that up. So here's the, wrong tab. So here's the example that we went through. We went through the example, which was FIFO, and you can see here the queue, you just keep tacking on to the end, and the front of the queue tells you where, when a page fault occurs, the new page goes, which frame the page goes into. And then that old frame goes to the end of the list on the queue. So that's the way the queue works. We'll take a look here now at the right next to it at the least recently used algorithm. First four are pretty much similar to, in terms of page faults, to the FIFO page replacement algorithm. But you can see here that your queue is actually being tacked on like a stack, basically, where it's 1, 2, 1, 3, 2, 1, 4, 3, 2, 1, because the new page coming in is the least recently used. In fact, it's just being used, so it's the least recently used. We can see, so you have each of those being put to the front, and then we have 2, which is in memory. But notice that with the situation where there is no page fault, you didn't actually update the queue here because it's first in, first out. And when there is not a page fault, there also isn't any update to the FIFO queue. But with least recently used, that new page that has been brought in, or that new and placed in a frame, goes to the front of the list, because now it is the one that has been least recently used, and we're going to pop them off the back, as you'll see later on in the example. So the next one is page 1, and so that goes in the front again because it's already, it's already in the frame. So there's no updates to the frame, but the number 1 frame gets put to the front because it's now the least recently used. Then we have 5, right? Yeah, 5. And so looking at our list, we see that frame 3 is the place to put it. So here's frame 3 getting the page 5 in there, and the other frames stay the same. And notice now that frame 3 is now at the front because that's where the new value went. Likewise with reference 6, it is, and again, another page fault because it's not in there. We look to the end of our least recently used list, and we pull out that it's frame 4 that's to be replaced. So frame 4 gets replaced with 6, and frame 4 gets put to the front of the list for least recently used. And then down the road here, you can see that this ends up with 10 page faults for this example, which is less than the FIFO example. And you can walk through that yourself. It's pretty much updating. You're always updating the least recently used with a new page reference, because that will, unless it already is the least recently used, but that will be put to the front of the list, and then the rest of the thing is just the straight replacement. We did have a question in class about Belody's algorithm. Oh, let's see, we got a. Oh, okay. Here's Belody's algorithm with the FIFO queue. Let's see here with FIFO. So we know that FIFO page replacement algorithm is susceptible to have it when you add more frames, you can end up with more page faults. This is actually the example taken from the textbook. They did have an example in the textbook of a set of references that with different. They actually had a graph with page references versus how many frames you have, and a graphing, and there was the anomaly that between 3 frames and 4 frames, the number of page faults actually went up when you added that extra 4th frame. Again, it's the same methodology that you go through, going through the FIFO queue of first of all, again, that when you don't have a page fault, the queue doesn't get updated, and that when you do have a page fault, you stick it on to the end, and the front of the queue tells you where on a page fault, which frame needs to be replaced. And so if you walk through the exercise, you can actually prove to yourself that with 3 frames, you end up with 9 page faults, but with 4 frames, you actually end up with 1 more page fault. For this example, you end up with 10. So this was a very surprising result. And when they were doing testing of various page replacement algorithms, and hence we have Belody's anomaly. So any questions on those examples? Again, you can go through those examples yourself and get more comfortable with it as well. And I do recommend that you go through the examples and see that you can follow what's happening. So the page we left off was on page buffering algorithms, but basically you're basically managing a cache, a buffer to act as a cache between it to try to minimize the cost of a page fault. And so you keep a pool of free frames when it's available. A frame is available, then you can use it right away without swapping out another page. And then we can read in the page from the free frame if the victim is evicted, but then comes back in and then requests memory space. If it's still in the pool, you can just grab it without having to reload it from disk because it's still in the pool. So there is the notion of keeping a reference to where it is in the free pool, and if it indeed is accessed again and creates a page fault, you can actually just go right to the free pool instead of swapping in from disk. The other advantage that you have with the buffering is that in background CPU threads, when cycles, when there's extra time available in the CPU, or If there's access to the disk, if you have a DMA, direct memory access mechanism, where the CPU is not involved, and that would be the ideal case, you could actually write out the contents of the free page pool to disk in the background. Basically, when the memory isn't being used by someone else, you can go ahead and write out the free pool storage into the hard disk, so you can take advantage of free cycles in memory access. The next bullet was just what I mentioned before about if it's referenced again before that free space has been reused, you can recover it. So, but the last bullet point is referencing that we are trying to reduce the penalty for that results if we incorrectly pick the best case scenario for the frame to be swapped out. The other thing is all these algorithms are trying to basically guess the future without having to know the future. And so they're using other values to try to determine what the future might look like. So least recently used, again, is the most popular, which says that if I've used it once really recently, it's likely I'm going to be using it again because of the way programs work and the locality of how code works in terms of using the same memory space over and over again. But there are cases where the application knows much better how the frames and pages are going to be used. And so a common example of that is a database. A database will generally have direct access to the memory and management of the memory, capability to manage the memory, because it has enough future knowledge about how the memory is going to be used. So oftentimes the database is actually circumvents the rest of the virtual memory, and so there's memory that's set aside just for the database application, and it is very prevalent with database design. Memory-intensive applications can do double buffering. Again, the concept of buffering to improve performance with the I/O, and trying to minimize the amount of I/O traffic that you need to do, because we know that that's expensive operation compared to memory accesses. And then the operating system can give direct access, be given direct access to the disk, getting out of the way of the applications, which is the raw disk mode. That's, again, pretty high level stuff when you're actually working with raw disk mode. Generally, you're working with the kernel as your intermediary and the virtual memory management software. And then we have bypass buffering and locking and things like that. So they're all different types of techniques, especially relevant to an application knowing better how they are going to access memory than others. The only other example that I've ever seen where there was direct control over the memory, or an attempt to do direct control over the memory outside of databases, was a finite element code that was basically the only software being run on the system. The finite element code was used for mechanical testing of collisions and things like that. So it was heavily used in the car industry, and performance was critical because it was such a heavy load on the system to run that application, and it used a lot of memory, and so it actually would manage its own memory, which made the application very hard to do. So it is usually used in extreme cases. Okay, so in terms of allocation of frames, each process needs a minimum number of frames to operate efficiently, that they will need at least a certain number of frames to be able to run without thrashing, which thrashing is constant paging in and out of pages. Example of that is the IBM 370, which, if you are into computer architecture, was a very interesting architecture. It had lots of parallelization features in it, and actually had an operating system that was oriented around these extended features. But it allowed 6 pages to handle the software, the SS move instruction in 6. So basically, what you can get from that is that there was hardware support and operating system built to handle efficiently the typical minimum number of frames that were necessary and the behavior of the applications. The maximum, of course, that you could have for a process is the total frames in the complete system. That would be a case where you would probably have the system pretty much dedicated to that application, because it would step all over all the other applications in a multi-user, multitasking system. There are 2 major allocation schemes: is fixed allocation and priority allocation. You can pretty much guess what that is, that everyone's given equal allocations, or they're given allocations based on the priorities of that process. And there are very many variations on this theme of allocation of frames. So I wouldn't worry in terms of quiz material. There won't be any quiz material on this, so just kind of keep this in mind as a general scheme if you have to worry about details. And here's just an example of how fixed allocation work, and also proportional allocation is another scheme. Again, it's just for your general knowledge. And then priority allocation is proportional scheme using priorities rather than just the straight size of how many pages a frame needs. And so the higher priority would get more, because we want to avoid page faults in that higher priority process. There's 2 general themes of global versus local allocation. One is that you select the frames based on the overall of all the processes. And part of this is that you'll have great variability in the performance, because with multiple processes, you don't know exactly how processes will interact with other processes, since you don't necessarily have control over what processes will be running on the operating system. And then we have local replacement, where each process manages its own memory frames, faults, and virtual memory, and so that the replacement policy is local to the process. That is generally less common, but it is an option. So I already mentioned earlier the concept of thrashing, and that's when a process does not have enough pages. The page fault is extremely high, and you can imagine a situation where you're spending all your time swapping pages in and out of the disk and back and forth, results in low CPU utilization, and it can actually result in the situation where your system will come to a screeching halt, and it will basically look like your system is locked up. I think a lot of you have probably seen this when you have a lot of different applications running and you have too many processes running for the amount of memory space that you have. Basically, the virtual memory management system just gets caught in this situation where it's constantly swapping pages in and out and not actually providing much progress for the task, because all the time is being spent thrashing or handling page faults. So demand paging is one of the basic locality models, and that's how you choose how to select algorithms and manage it. So thrashing occurs when the size of the locality or the set of frames, or sorry, not frames, pages that you're using are greater than the total memory size. You will definitely lead to this will lead to thrashing, and this is, again, like I said, typically resulting from lots of processes running, or the other effect can be due to a high priority process needing a great deal of pages and basically blocking out all the other processes' desire for memory. So basically it's hogging all the resources in terms of memory. So again, remember, thrashing is when a process spends more time paging than actually producing, executing and getting progress. Memory map files is simply a scheme where you're reading and writing to a file, but in fact, in actuality, it's been mapped to memory. So again, it basically looks like disk I/O, but is much faster because it's being used in memory. And so there's all kinds of techniques for doing that. And there's, of course, great advantages. You can write out to a file with in and out of a file with much greater performance. Of course, this assumes you have the memory space necessary to do this, but the other issue is what happens with a power failure. You may lose information that you think has been permanently stored in a file, and so you actually have to have mechanisms to periodically flush the information from the memory to the file, the actual physical file on the disk, in order not to lose data during a power failure. So things to keep in mind. And so this is just a pictorial diagram of what I was talking about, pretty straightforward. And then one thing that may come to mind is, what about the kernel? Well, the kernel is definitely treated very differently from user memory. Generally, it's allocated from a free memory pool, and because it behaves very much like a real-time operating system where there are certain criteria or demands of quick completion, because you expect kernel calls to be quick and then out, and allowing for another kernel process to happen. So again, common to real-time operating systems, a free memory pool is generally used for managing kernel memory. Another twist is the buddy system, which is basically grouping together frames so that you access it in terms of power over 2 allocations. And so when smaller allocations need it, then you can use a lower power of 2. And when a big allocation is needed, you use a larger power of 2. And there you now are specifying or allowed to dictate the locality, because you know that all of the data is within this variable space, if you want to call that, chunk of memory. And so it'll either all be in memory as you're actively processing it, or it all will be paged out to the disk when eventually there aren't any more accesses in that area. So the advantage is that You quickly coalesce unused chunks into larger chunks because of the way you select it. The disadvantage is that you can have large pieces of fragmentation because allowing these power of 2 allocations of frames can allow a process to grab a big chunk, and now you end up with all these different piece size fragments all over your physical memory frames. So this is another scheme that can happen. The other is a slab, and this is a special case strategy. It's when a slab is one or more physically contiguous pages, and the cache consists of one or more slabs, and each cache is unique to a kernel data structure. So each cache is tied to something specific in the kernel. When the cache is created, you fill the objects marked as free. When structures are stored, the objects are marked as used. So here's the idea of the free pool, right? And then if a slab is full of used objects, the next object allocated comes from the empty slab. If no empty slabs, a new slab is allocated. The benefits include that there's no fragmentation, and you have fast memory request satisfaction. But this does take into account or use some knowledge of the applications and the processes using the memory. So one example from your text is Linux. There's a slab allocator, and the process descriptor is struct task structure. So here, that's your slab, and it's approximately 1.7 kilobytes of memory. Of course, as you can imagine, with different versions of Linux, it may be different. And then a new task allocates a new structure from the cache, and it will use the existing free structure task struct. And so we know that basically there's a pool of that size, which is the slab. So the slab can be in 3 possible states. It's full, all is used; empty, all is free; and then partial, there's a mix of free and used slabs, or free memory. Upon request, the slab allocator uses free struct in partial slab. If none, it takes one from the empty slab. If no empty slab, it will create new. It creates new empty elements for the slab. But again, this is pretty detailed. It's generally pretty sophisticated and is written in direct connection with the kernel. And I'm not going to quiz you on this level of detail, so don't worry about this in terms of the quiz. There are various slab variants. The text goes into, well, slab started in Solaris, and it's now become a widespread technique used in kernels for various operating systems. And it turns out that Linux 2.2 has slab, but it has also things called slob and slub. And I'll refer you to the text to see the details of those particular algorithms. So that completes our coverage of virtual memory. I know that it was sort of spread out over a few lectures. Let me quickly go through what's important for you to know for the quiz. So again, make sure you know what the purpose of virtual memory is, what the justification, why do we want to use virtual memory. Make sure you know this slide and the information related to this slide. Quickly going through. We want to know the page replacement algorithms. FIFO and least recently used for sure. Optima, it would be nice to know too, but you do want to make sure you know FIFO and least recently used. It's pretty straightforward. And then that Balinese anomaly does exist and, in fact, can occur in the FIFO page replacement algorithm. And then basically, I want you to be able to walk through an example of a bunch of memory accesses like we went through in that expels brief sheet and on this optimal screen and the least recently used screen about how pages are selected for replacement. And which frames they come from and how you select which frames that you're going to pull it out for and replace. The other thing to keep in mind, I've said it a few times, is the least recently used algorithm is the most commonly implemented page replacement algorithms. There are other algorithms, of course, like you know, but least recently used is the most popular. In terms of the enhanced second chance algorithm, I'm going to really quiz you on the intricate details of how the enhanced chance algorithm is layered on. But do keep in mind that we have a ordered set, the reference, which is how recently has it been referenced, and modify. So you have the ordered pair or tuple, where you also keep track of it, whether the page has been modified, and then take note that scenario number one, where both hasn't been recently used and it hasn't been modified. So basically there is no page swap out to disk necessary. That would be the ideal case. And then number four is the worst case, where it's been recently used and modified. That would be the worst case. So that's that's the key thing that I want you to know from that, is that there's this two pair, and that case one is the best case and case four is the worst case. Oh, and then keep in mind what thrashing is, which is when a process is spending more time paging frames in and out, and it's hampering progress because you're spending more time doing that than actually executing the process. So that's the concept of thrashing. Okay, so that's the main things I want you to know from the virtual memory topic. Again, the quiz, I think, is scheduled. If not, it should be pretty soon. I guess the quiz for main memory I scheduled already, but I'm not sure I did the quiz for virtual memory. Again, the quizzes are open book and open notes, but please, on the honor system, please don't go on the web and start Googling for answers. So any questions on virtual memory? Or again, any questions come up with the class in general? All right, so without any other questions, I don't see any questions on the chat, we will move on to mass storage structures. So what are we talking about for mass storage structures? Most commonly, we think of magnetic disks, but there are all kinds of different forms through history and currently of mass storage, and one of the most recent is non-volatile memory disks. So that is one of the newer things that are coming on the spectrum of commonly available mass storage solutions. So when we're talking about mass storage, we're talking about large amounts of storage beyond the capability of memory. And because of that, since you want to have large portions of storage, the cost of it is below that of memory. So you have the two aspects of non-volatility and then the cost of the storage medium. So again, the bulk of storage right now with modern computers is magnetic disks, but like I said, we do have the non-volatile memory drives as well. Characteristics of a storage device is that it rotates from 60 to 200 times per second, and I wonder if that might be a higher number now because this is probably dated information. And there are two key things that are involved with the transfer rate is the rotation, how fast it goes, but also we're looking at the seek time, which is there's an arm assembly that goes radially along the disk, either in or out for each of the different tracks. So your access time becomes the rotational latency plus the seek time. The seek time in general will be the larger component of that positioning time. One of the downsides is a hard disk, is a disk crash, head crash, and that's when the head actually makes contact with the disk surface. And I added here that's bad. Basically, you will lose data. And who knows how the distance is established of the read and write head above the hard disk? Is anyone familiar with how that happens? Okay, so I don't see any responses. So basically, it's actually flying above the surface of the disk. It's actually using aerodynamics and the spinning nature of the disk that is actually floating on this cushion of air and literally flying. So generally, you will have a landing zone where basically the disk comes down when you actually stop the drive in a controlled manner, which determines where it will go when it's shut off so that it doesn't do damage. But basically, you can see that would be a potential cause of hard disk crashes, is that miss the landing zone or you drop the drive, all those kinds of things, that it's sitting on, it's actually literally flying over the top of the surface of the disk. We have both fixed and removable forms of these. We generally don't see too many removable magnetic medium drives so much anymore. I bet none of you have heard of a Bernoulli box, but basically those were removable hard disks. Now we have optical disks that are much more common in terms of removable. And then if you go back far enough, we have floppy drives. And floppy drives, on the other hand, the reading head actually is like a record player and is actually physically moving on the disk. It actually is not floating above the material, but is actually on the disk for floppy drives, in contrast. And then the drive is commonly attached to some type of I/O bus. We have EIDE, ATA, SATA, USB, fiber channels, SCSI, FireWire, which is amazingly fast. But we have various bus structures for handling the I/O between the CPU and memory and the disk. And then the host controller in the computer talks to the bus, uses the bus to talk to the disk controller, which is built into the drive or storage array. So the drive or storage array actually contains the disk controller, and the host controller in the computer then talks to the disk controller, telling it what it needs to do. Again, we have direct memory access, where the CPU can be, once the request has been initiated, it can be taken out of the loop, and the drive can then access memory or steal memory cycles and store it directly to memory and give an interrupt when it's available. So that takes us to just about to the end of our time. Does anyone have a question about the lecture material or the class in general? Okay. So not hearing anything, I'm going to go ahead and stop the recording, and